Okay, so let's talk about continuity. Now, if you're at this video and you're looking for a definition of continuity in terms of calculus, if you're a calculus student, particularly a calculus 1 student, and you have a homework problem and you're trying to figure out how to figure out if something's continuous or not, maybe you're looking at a graph and you're like, how do I figure out if this is continuous? I'm in a calculus class, need some help. This is not the video for you. This is going to be a video more on the analysis version of calculus. This is going to be a much higher level discussion about continuity here than it would be in a calculus class. So if you are in a calculus class and you're needing help with continuity, I advise you to please switch over to the Calculus 1 section of the YouTube channel, and there will likely be a continuity video there that can help you out better. But for those of you that are in analysis and you were looking for an analysis description of continuity, you're in the right place. Let's actually start out with a calculus definition of what continuity is, though. Let's say we've got a point right here, and I don't know what x value that is because it's in a strange location. But let's just say we're trying to figure out if this point is continuous in this graph y equals x cubed. Well, we all know from our calculus class days that this is continuous there. This is a polynomial function. We know polynomials are smooth functions. You don't have to raise your pencil to draw them. And you also know from the simple mathematical definition of continuity that, you know, the limit of f of x as x approaches whatever this x value is here, you know that the limit here is equal to the value of the function here. And so because of that, you know from calculus that this is continuous at this point. And so we understand the very basic definition of calculus, continuity in terms of calculus. We understand that. But how do you take the calculus explanation of what continuity is and translate that into a deeper understanding of how analysis would explain continuity? And so to do that, let's first look at just the definition that I'm sure you've seen in your analysis class. And that is this statement right up here at the top. And this just says, consider f to be something that maps D to R, so your domain goes to R, with D being a subset of R. So again, your domain is just some subspace, some subset of the real numbers. So now let's suppose we have some A that's in our domain. So f is said to be continuous at A if for any arbitrary epsilon greater than 0, there exists an arbitrary delta greater than 0 such that f of x minus f of A in absolute values is always less than epsilon if x minus A in absolute value is less than delta, and that x is in D. Now for this definition of continuity, you have to remember that this is a local property, and so that x being in D, and in particular the A being in D, is very important for this. Something you've probably heard in your analysis class is that if you're proving continuity in one of these situations, the delta value that you get is always going to be in terms of epsilon, but it's also going to be in terms of A. And that's very important because if it's not in terms of A, you're proving uniform continuity, which is a slightly different version of continuity, and we'll talk about that in future videos. Okay, so now we've got the basic definition of continuity. We understand from calculus what continuity is, and we have the analysis definition of continuity. So let's spend just a minute or two trying to figure out just what this definition actually means, because if you don't understand what the meaning of this is, you're never going to be able to prove that different things are continuous and further in different analysis examples that I'm sure you have for homework problems. So you can kind of dissect what you have here. So this for all epsilon greater than 0. This is always going to be at the beginning of all your proofs. And oops, that's not a highlighter, that's a marker. Let me fix that. This is going to be at the beginning of all of your proofs, and this is extremely important. So this, and then the f of x minus f of A in absolute value is always being less than any arbitrary positive epsilon value. What this is right here is, if you look at this chart, this is just some arbitrary point that we made up. This is just at a point A, f of A, so again, very arbitrary. And let's say you're trying to prove that something is continuous at this one point, because remember, this definition is local. So this means you're proving something's continuous at one location, not uniformly across the entire domain. So let's say you're trying to prove that this one point is continuous. Well, this f of x minus f of A absolute value, this difference here always being bounded by epsilon. And if you're forcing epsilon to be positive and arbitrary, that means you can make epsilon any positive number you want to. And it can get infinitely close to 0, but it can never be 0. And so what that means is you have your f of A over here on this axis. And let's say you choose f of x to be right here. or you choose f of x to be right here. So the positive and the negative iterations of f of x. So that makes that f of x minus f of a absolute value difference to be this or to be this. And in either case, the biggest that can be here is epsilon. But epsilon is something that you're able to change. And the reason you're able to change that is because of this statement right here you put at the beginning of your proof. And so as you continue to make epsilon smaller and smaller and smaller, you're forcing this f of x minus f of a difference to be smaller and smaller and smaller. So over time, you're able to force this to bound like that. And then if you choose an even smaller epsilon value, you can bound this even further. And you can see you can continuously make this smaller and smaller and smaller until you force this one point to be the only thing left. Similarly, you can do the same thing on this x-axis. And the x-axis is this statement right here. So this is where you're bounding the x minus a difference by delta. And if you continue to bound it infinitely, you can make these bounds closer and closer and closer until you get to the point where the only thing left is a. And because you're able to bound it in such a way, you can prove this statement to be true. That if you pick a delta that depends on what epsilon is and depends on what a is, you fix this right here. And whenever you fix this right here, it forces the f of a to be fixed as well. And that will complete the statement that you're trying to prove. So whenever you're writing these really convoluted proofs and you're not really understanding, why does epsilon have to be arbitrary? Why does delta have to be arbitrary? Why do I need this statement? Why do I need this statement? And you're not really understanding what all those pieces mean. If you think about it in a graph form like this is essentially what you're doing. You're making it to where it's possible to infinitely squeeze the x-axis. And because you're infinitely squeezing that x-axis around the point A, you're able to do this. It forces the y-axis to squeeze around f of a. And that's how you're able to prove local continuity using this analysis definition.